Imagine you're looking into a mirror. Everything is reversed. Left becomes right, and right becomes left. This simple reflection is how we typically think about symmetry, a one-to-one correspondence, a perfect balance between two sides. It's a concept so fundamental that it has shaped our understanding of nature and the universe, driving scientific breakthroughs in physics, mathematics, and even art for centuries. But symmetry, as it turns out, isn't just a superficial feature of the world we observe. It's deeply embedded in the way we formulate the laws of nature. Over the past century, symmetry has become a guiding principle for physicists, trying to understand everything from the behavior of subatomic particles to the vast structure of the cosmos. One of the most compelling questions that arose from 19th and 20th century physics was, how do the laws of nature stay the same no matter where we are, when we are, or in which direction we're moving? Physicists sought symmetry to make sense of why these laws don't seem to favor one direction of time over the other. If you run the equations of Newtonian mechanics, or even Einstein's theory of relativity backward, they still make sense. Time is symmetric in the equations. Whether you're looking forward or backward, the underlying physics doesn't change. This led to a dualistic understanding of nature. For every force, there's an opposite. For every particle, an antiparticle. For every action, an equal and opposite reaction. These dualities provided a powerful framework for understanding the universe. Symmetry gave us the idea of balance, predictability, and conservation. For example, the conservation of energy and momentum relies on the symmetrical behavior of systems over time. And in quantum mechanics, symmetry helped predict the existence of antimatter, balancing the equations that describe particles. But this framework wasn't without its problems. As our understanding of physics grew more sophisticated, we began encountering puzzles that symmetry, at least in its dualistic form, couldn't fully solve. The most glaring issue was time itself. Yes, equations may work in reverse, but the world doesn't. Time, as we experience it, moves in one direction. We live in a universe where entropy increases, where things decay and evolve. If the laws of physics don't pick a preferred direction for time, why do we? This puzzle led scientists on a quest to find deeper symmetries, ones that could explain not just simple dualistic pairs, but more complex, interconnected systems that could account for the flow of time, the emergence of complexity, and the inherent balance of the universe. We needed a way to move beyond binary oppositions and consider more intricate interactions. And this is where the triad comes in. What if, instead of thinking about balance as a back and forth between two forces, like a pendulum, we began to think about it as the result of three interdependent elements, each influencing and constraining the others? Triadic symmetry offers a richer, more nuanced way to understand how systems achieve balance. In a triadic model, the third element isn't just an afterthought, it's essential. It serves as the constraint, the mediator that stabilizes the other two forces or variables. Without it, the system would collapse or spiral out of control. It's not just balance between two opposites, but balance through a third constraint that ties everything together. For example, think about how we experience force in the physical world. It's not just the product of mass and velocity, as you might think. It's mass times acceleration. But acceleration is itself velocity over time. Time is the hidden third element that constrains the interaction between mass and velocity, allowing force to emerge as a balanced entity. We see this same triadic structure in many physical laws. The ideal gas law, which relates pressure, volume, and temperature, functions because the third element, volume, constrains how pressure and temperature behave. Change the volume of a container, and you immediately affect both the pressure and the temperature. Each of these elements is interdependent and constrained by the third, creating a stable, balanced system. The limitations of dualistic models also show up in more complex systems like quantum mechanics and cosmology. In traditional physics, the introduction of antimatter was essential to maintaining symmetry in equations, leading to an elegant but sometimes problematic idea: for every particle, there's an antiparticle. But antimatter, as predicted by these equations, is incredibly rare in the universe. and its interactions seem more like mathematical necessities than physically pervasive realities. But what if we could reframe this need for opposites? In our triadic model, vacuum potential energy replaces antimatter as the stabilizing force. Instead of needing a mirror image for every particle, the vacuum itself, the so-called empty space, provides the necessary balance. The universe doesn't need a one-to-one match of matter and antimatter. Instead, we see a continuum where manifested particles and latent potential, vacuum energy, dynamically balance each other in a triadic relationship. In this triadic framework, we begin to see the universe not as a set of dual oppositions, but as a system of self-sustaining patterns that emerge from three-way interactions. This applies not only to fundamental forces and particles, but also to more complex emergent systems like life, consciousness, and even social dynamics. Each of these systems can be understood in terms of triadic relationships, where two variables are balanced by a third, ensuring stability and evolution over time. In biology, for example, the interaction between genetic information, environmental stimuli, and metabolic processes forms a triadic system that maintains the homeostasis of living organisms. In cosmology, we could look at the interaction between mass, velocity, and gravitational curvature as a triad governing the dynamics of celestial bodies. Across all these scales, triadic symmetry helps explain how balance is maintained through the dynamic interplay of three forces, each influencing the others in an intricate dance of interdependence. Now let's take this triadic model and see how it applies across different scales, from the smallest building blocks of the universe to the most complex systems we know, like life itself. One of the most exciting aspects of this framework is that it doesn't just apply to subatomic particles or forces in isolation. It operates everywhere, at every level of complexity, creating self-sustaining patterns that allow systems to maintain stability and function. Let's start small. In the world of quantum mechanics, the interactions between particles, fields, and forces are governed by fundamental triads. Take quantum chromodynamics, QCD, for instance. We've already mentioned that quarks interact via three color charges, red, blue, and green. This triadic relationship is what keeps protons and neutrons stable, with the strong force balancing their interactions. Any imbalance in the color charges would destabilize the particle, but the system achieves stability through this triadic interaction, ensuring that these particles stay bound together within the atomic nucleus. But what's interesting here is not just the balance itself, but how this interaction is self-sustaining. If one color charge shifts or changes, the other two immediately adjust. This triad doesn't require external intervention to keep it balanced. It dynamically adjusts itself to maintain stability. This is the essence of self-sustaining patterns. Systems that adjust internally to external changes in a way that maintains balance. Now, let's scale this up. Think about thermodynamic systems where energy is exchanged in the form of heat and work. Here we have another triadic relationship: heat, work, and internal energy. The first law of thermodynamics tells us that the change in a system's internal energy is equal to the heat added to the system minus the work done by the system. Once again, the system sustains itself by balancing the flow of energy between these three components. The system doesn't need an external force to create equilibrium. This triadic relationship inherently allows the system to respond to changes in heat and work while maintaining its internal energy. Now, imagine scaling this further to something as complex as an ecosystem. In ecosystems, energy flows, species populations, and environmental conditions form a triadic relationship that sustains life. Energy from the sun flows into the ecosystem, feeding primary producers, which in turn support herbivores and predators. At the same time, environmental conditions, like temperature, water availability, and nutrient levels, constrain and shape these interactions. If one element shifts, say a sudden change in temperature, the entire system responds, adjusting energy flows and population sizes to re-establish equilibrium. Once again, the system sustains itself dynamically, maintaining a balance between its components. At every level, from the quantum to the thermodynamic to the ecological, we see this triadic balance at work, enabling systems to sustain themselves over time. The magic of these patterns is that they emerge naturally from the interplay of the three components. No single element dominates. Instead, each one contributes to the stability of the whole. And this isn't confined to physical systems. Social, economic, and biological systems all exhibit similar triadic patterns that maintain balance while allowing for dynamic change. But how do these self-sustaining patterns remain stable over time? What keeps them from falling apart under pressure, change, or disruption? This brings us to the concept of topological stability and homeostasis, ideas that help explain how systems maintain their structure even as they evolve. Let's first talk about topological stability. Topology, in simple terms, is the study of how shapes and structures maintain their integrity even when they are deformed. Imagine a rubber band. You can stretch it, twist it, or bend it, but it retains its essential shape unless you cut it or tear it apart. Similarly, systems that exhibit topological stability can withstand changes without losing their fundamental properties. In physics, this concept is analogous to the behavior of solitons, self-reinforcing waves that maintain their shape even as they travel through a medium. Solitons are fascinating because they resist dissipation. Unlike regular waves, they don't break down or lose energy as they move. This kind of persistence through change is precisely what we see in triadic systems. The balance between the three components creates a stable structure that can adapt to changes but doesn't lose its overall form. Think back to our example of force in Newton's second law. If we alter mass or acceleration, the force adjusts accordingly to maintain the relationship. This isn't a static system, but a dynamic one, where changes don't lead to breakdown but instead drive an adaptive response that sustains the system's balance. The system remains stable because it's topologically robust. It can bend without breaking. But beyond physics, this concept of topological stability applies to more complex systems like biology. One of the best examples of this is homeostasis in living organisms. In biological systems, homeostasis is the ability of an organism to maintain internal balance despite changes in the external environment. This could be something as basic as maintaining body temperature in the face of fluctuating weather, or as complex as regulating blood sugar levels through the interplay of insulin, glucose, and metabolic processes. What's remarkable about homeostasis is that it too operates through triadic relationships. Take the regulation of blood sugar. The pancreas, glucose, and insulin form a triadic system that adjusts dynamically to keep sugar levels stable. If glucose levels rise, the pancreas releases insulin, which helps cells absorb glucose, bringing the system back into balance. This dynamic process ensures that even when the system is under stress, like after eating a large meal, it can restore balance, sustaining life. The stability we see in these systems doesn't come from rigid structures or external controls, but from the internal feedback loops that constantly adjust the relationships between the system's components. Each element of the triad exerts influence on the others, and when one changes, the system adjusts to maintain equilibrium. This self-adjusting feedback is the hallmark of homeostasis, and it's why triadic systems are so stable over time. Now let's scale up again. In cosmology, we encounter the same kind of self-sustaining stability when we look at the gravitational forces that govern galaxies. The interaction between a galaxy's mass, velocity, and gravitational curvature forms a triadic relationship that determines its structure and behavior. The galaxy's rotation is balanced by its mass and the curvature of space-time, with gravity serving as the constraining force that holds everything together. Even in the dynamic, evolving universe, these triadic relationships ensure that galaxies don't collapse into chaos. They maintain their form over billions of years. What's common to all these examples, from quantum mechanics to ecosystems to galaxies, is the idea that stability isn't passive, it's active. It's the result of constant dynamic feedback where each element of the system adjusts to changes in the others. And at the heart of this stability is the triadic structure that governs the interaction. These systems can withstand disruption because they don't rely on static balance. They rely on adaptive topological stability that allows them to change and evolve without losing their fundamental structure. So whether we're talking about subatomic particles or living organisms, triadic symmetry provides the foundation for both stability and adaptability. It's the mechanism that allows systems to remain stable while responding to changes, and it's the reason why these systems persist across time and scales. Now, let's shift our focus to one of the most intriguing concepts in modern physics, antimatter. When it was first predicted by Paul Dirac in the early 20th century, antimatter seemed like a brilliant, almost poetic solution to a symmetry problem in quantum mechanics. The equations that describe particles, like electrons, didn't quite balance without the existence of a mirror counterpart, an antiparticle, identical in mass but opposite in charge. This prediction was later confirmed with the discovery of the positron, the electron's antiparticle. And from there, the idea took off. Every particle, it seemed, had an antimatter twin. But as elegant as this symmetry appeared mathematically, it soon introduced new puzzles. If every particle has an antiparticle, why don't we see as much antimatter in the universe as we see matter? Why does our universe appear to be made almost entirely of matter, with antimatter so rarely observed? To make things more complicated, when matter and antimatter meet, they annihilate each other, converting into pure energy. This raises the question, how did the universe survive long enough to form stars, planets, and life if equal amounts of matter and antimatter were created in the Big Bang? Why didn't everything annihilate immediately? These were fundamental issues for a dualistic model of symmetry. Antimatter had to exist to balance the equations, but its scarcity raised deep questions about the nature of reality. What if, instead of requiring a one-to-one counterpart for every particle, we took a different approach, one that doesn't rely on strict binary oppositions? This is where the triadic model offers a new way of thinking about the role of antimatter in the universe. Instead of seeing antimatter as the mirror opposite of matter, what if we viewed it as part of a broader triadic system, where balance is achieved not through direct opposition, but through the dynamic interaction of three elements? In our triadic model, antimatter is reinterpreted as part of the vacuum potential energy, the underlying field of possibilities that exists in every system. Instead of antimatter being a separate mirror universe that exists alongside matter, we see it as a kind of latent potential within the fabric of space itself. This reimagining solves some of the paradoxes posed by the dualistic view of antimatter. Here's how it works. In our triadic framework, matter is one part of the system, the vacuum is another, and the third element is the dynamic process of interaction between them. The vacuum isn't a void or absence, it's a reservoir of potential energy. This potential doesn't need to manifest as antimatter to balance matter. Instead, it acts as a stabilizing field, ready to influence interactions as needed, but not requiring the existence of an equal amount of antimatter to cancel out matter. Imagine the vacuum as a kind of latent potential that's always there, influencing the behavior of particles without needing to take form itself. This continuum of energy that permeates the vacuum is what balances the equation, not a physical mirror image counterpart for every particle. By reinterpreting antimatter this way, we remove the need for a destructive duality where particles and antiparticles are constantly poised to annihilate each other. In this triadic system, negation is not about two forces canceling each other out, as in the case of matter and antimatter annihilation. Instead, negation is better understood as vacuum potential energy, the unseen but always present possibility within the system. For example, when you look at quantum field theory, particles are often described as excitations in a field. In this view, particles, matter, are just one state of the field, while the vacuum represents another latent state. The triadic model allows us to think of vacuum energy as part of the same system rather than something that opposes particles directly. It's a balancing force, but not a destructive one. The vacuum isn't nothing. It's a source of potential available to stabilize and interact with matter without needing to manifest as antimatter. This reinterpretation of antimatter resolves many issues that arise from the traditional dualistic approach. We no longer need to ask why we don't see equal amounts of matter and antimatter in the universe. the vacuum potential takes over the role of stabilizing the system, allowing the universe to maintain balance without annihilation. This brings us to a deeper philosophical shift that underpins the triadic model, the energy continuum. In traditional physics, we often think of forces and particles in terms of binary opposites. Matter and antimatter, positive and negative charge, north and south poles, they are all part of a dualistic framework. But this way of thinking creates hard boundaries between entities that are, in reality, part of a continuous spectrum. In a triadic model, we see energy as existing on a continuum. Instead of rigid opposites, we understand that matter and vacuum potential are two aspects of the same system. The balance between them is mediated by a third dynamic process that connects and stabilizes them. This continuum-based view provides a more fluid and integrated way to understand how the universe operates. Let's return to the idea of force as an example. In Newton's second law, force equals mass times acceleration. But acceleration itself is a change in velocity over time. There is no hard boundary between these components. Time is the constraint that links mass and velocity, allowing force to emerge as a balanced result of their interaction. Similarly, in our triadic model, energy flows between matter and vacuum potential, constrained by the dynamic process that links them. There is no hard divide, no strict opposition, just a continuous flow of energy that keeps the system stable and balanced. This also changes how we think about entropy and order. In a dualistic framework, we often view entropy as the opposite of order, a force that drives systems toward chaos and disorder. But in a triadic system, entropy becomes part of the continuum, a balancing force that ensures systems can adapt, evolve, and maintain stability over time. It's not the enemy of order, but a necessary part of the dynamic balance that sustains life, motion, and change in the universe. A triadic approach also removes the idea of destructive annihilation from the equation. In the dualistic model, matter and antimatter exist in constant tension, where their interaction results in mutual destruction. But in a triadic model, the relationship between matter and vacuum potential is not antagonistic. Instead, it's complementary. The vacuum provides the latent energy that can stabilize and sustain matter without needing to annihilate it. In this way, the universe becomes a place of dynamic balance, where energy is not constantly being destroyed or opposed, but is instead flowing smoothly across a continuum. Matter and vacuum potential are part of the same whole, interacting in a way that maintains the system's homeostasis without the need for destructive processes. This is a more holistic and, in many ways, more optimistic view of the universe. A universe where balance is maintained not through opposition, but through integration. This idea of an energy continuum isn't limited to the quantum or cosmological realms. It has profound implications for how we think about complex systems in general. In biology, for instance, the triadic relationship between genetic information, environmental adaptation, and energy flow creates the balance that allows life to evolve and sustain itself. There's no destructive opposition, just a continuous process of adaptation and balance that ensures the survival and evolution of living organisms. In economics, we might see similar patterns. The triadic interaction between supply, demand, and market regulation creates a dynamic system that can maintain balance even in the face of external shocks. The key to stability in all these cases is not the opposition of forces, but the interaction of three elements that dynamically adjust to maintain balance over time. Ultimately, this triadic model transforms how we think about balance, energy, and stability in the universe. Instead of seeing the world in terms of opposites locked in conflict, we start to see it as a continuum of dynamic energy flows, where balance is achieved through interaction, mediation, and integration. This shift from a dualistic to a triadic perspective doesn't just solve some of the fundamental puzzles of physics, like the nature of antimatter. It also gives us a deeper understanding of the universe as a place of harmony, where balance is achieved through continuity and flow, not opposition and destruction. Let's turn to some examples. Let's begin with something familiar, Newton's second law of motion. You've probably heard the equation force equals mass times acceleration. But what does this really mean? In everyday terms, force is what makes something move. It's the push that gets a car rolling, the kick that sends a soccer ball flying. But here's where it gets interesting. Acceleration isn't just how fast something moves, it's how fast the speed itself is changing. It's velocity over time. And in this triadic relationship, time is the hidden constraint. Without time, there's no acceleration. The faster something speeds up, the shorter the time interval, and the greater the force needed to make that change. Time is what holds this system together. It constrains how mass and velocity interact. It's not just a background variable, it's the third element in this triad, ensuring that when mass changes or acceleration shifts, force adjusts dynamically. Time, in this sense, plays the role of the mediator that makes balance possible. Now, imagine a balloon. As you blow air into it, the balloon expands. You're increasing the volume. But inside that balloon, something fascinating is happening. Pressure and temperature are interacting in a delicate dance. This brings us to the ideal gas law, which connects pressure, P, volume, V, and temperature, T. Think of this triad as a system where the amount of space available, volume, acts as the constraint. If you squeeze the balloon, reducing its volume, the pressure inside goes up. If you heat the air, increasing the temperature, the pressure rises again unless the volume can expand to compensate. In this triad, volume is the key mediator. It's the third element that ensures balance between pressure and temperature. Without volume to hold it all together, the system would collapse. Volume doesn't just contain the gas, it governs how the other variables behave, acting as the constraint that keeps everything in dynamic equilibrium. Change the volume, and both pressure and temperature have to shift to maintain balance. Another perfect example of how a triadic system operates. Next, let's think about electricity, specifically Ohm's law, which links voltage, V, current, I, and resistance, R. It's the law behind everything from your smartphone charging to your house's electrical wiring. Voltage is the push that drives electricity through a wire. Current is the flow of electrons. But here's the catch. It's not just about how hard you push or how fast the electrons flow. There's a third element, resistance, which acts like a barrier that slows down the current. Think of resistance as the friction that constrains the relationship between voltage and current. In this triadic system, resistance is the mediator, balancing the flow. If resistance increases, current decreases for the same voltage and vice versa. Resistance doesn't just hinder, it regulates, ensuring that voltage and current interact in a controlled, stable way. Without resistance, the system would be chaotic, just as removing the constraint in any triad throws it out of balance. Let's zoom out now, way out, to the solar system. Kepler's third law tells us something fascinating about how planets move around the sun. The square of a planet's orbital period, how long it takes to orbit the sun, is proportional to the cube of the semi-major axis, its average distance from the sun. But what holds this relationship together? It's gravity, the third invisible force that constrains both time and distance. If a planet moves farther from the sun, the gravitational pull weakens, and the planet takes longer to complete its orbit. Gravitational force acts as the mediator, maintaining balance in the triadic relationship between time and distance. Just like the triads we've seen in other systems, gravity isn't an afterthought. It's the critical element that binds time and distance together. Without gravity acting as the constraint, the entire system of planetary orbits would break down. It's gravity that ensures a stable balance, allowing the planets to move in predictable, sustained patterns over time. Now let's dive into the world of thermodynamics. At the heart of thermodynamics is the idea that energy moves between different forms: heat, work, and internal energy. According to the first law of thermodynamics, the change in a system's internal energy equals the heat added to the system minus the work done by the system. But here's the triadic magic. Internal energy is the mediator that balances the exchange between heat and work. When you add heat to a system, some of that energy goes into doing work, like lifting a piston in an engine, and the rest is absorbed as internal energy. If the system loses heat, internal energy drops, affecting how much work the system can perform. Internal energy is the stabilizing force that connects and regulates heat and work. It's not a passive bystander, it's the third element that mediates how the system responds to energy flows, ensuring that the system doesn't spiral out of control. This triadic relationship is what keeps engines running, climate stable, and even your body's temperature regulated. Finally, let's tackle one of the most profound frameworks in all of physics, Maxwell's equations, which describe the relationship between electric fields, magnetic fields, and space-time. These equations show how electric and magnetic fields don't just exist in isolation, they constantly interact. A changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. But here's the twist. Their relationship is constrained by space-time. The very fabric of space and time is the third element that mediates how these fields interact. Without space-time, the fields wouldn't propagate, and the intricate dance between them would collapse. It's this constraint that allows electromagnetic waves, light itself, to travel through the universe. In this triad, space-time is the hidden force, the framework that keeps electric and magnetic fields in balance. It determines how fast they move, how they interact, and how they transfer energy across vast distances. Without this constraint, light couldn't travel, wireless signals wouldn't work, and the fundamental forces of the universe wouldn't hold together. In each of these examples, whether it's Newton's laws, the ideal gas law, or Maxwell's equations, triadic symmetry emerges as a universal principle. It's not just about balancing two variables, but about how a third element constrains and mediates those interactions, allowing systems to remain stable, adaptable, and self-sustaining. This triadic structure appears everywhere, from the smallest subatomic particles to the largest galaxies, showing us that the universe doesn't work on simple dualities. It operates on the dynamic balance of three interdependent elements, each essential to the system's stability. As we bring this exploration of triadic symmetry to a close, let's step back and see how all of these insights connect into a single, unified framework for understanding the complex systems that shape our universe. What we've seen throughout this journey is a recurring theme. Whether we're dealing with the force of a moving object, the pressure inside a balloon, or the way planets orbit a star, stability and balance are rarely the result of simple dualities. Instead, they emerge from a triadic interplay, a dynamic interaction between three essential components, with one acting as the constraint or mediator that keeps the system in balance. This triadic structure offers us a more comprehensive way to understand how systems adapt, how they evolve, and how they maintain homeostasis in the face of change. It helps explain not only fundamental physical phenomena, but also the more complex emergent behaviors that occur in biological systems, ecosystems, and even social dynamics. One of the most profound insights from this model is the rethinking of negation, no longer as a destructive force, but as a stabilizing influence. In dualistic models, opposites are often set up to cancel each other out, like matter and antimatter annihilating each other. But in a triadic framework, negation takes on a different role. Think of the vacuum potential energy we discussed earlier. It's not simply the absence of matter, it's the latent potential, the unseen stabilizer that balances the system. In this way, negation doesn't destroy the system. It supports it by providing the foundation from which matter and energy can interact. This is the subtle role of the third element in all triadic relationships. It keeps the system from spiraling into chaos by absorbing tension and maintaining balance. Whether it's the vacuum stabilizing matter in the universe or resistance regulating electrical currents, negation as stability is a profound shift in thinking. It allows us to see systems not as fragile, needing constant external correction, but as inherently self-regulating. They contain within them the mechanisms to adapt, evolve, and persist over time. This triadic framework offers a new way to see the universe, not as a collection of opposites in conflict, but as a system of dynamic balance. From the smallest scales in quantum physics to the vast, evolving structures of galaxies, stability isn't achieved by forces battling it out in opposition. Instead, stability emerges from the interplay of three components, each shaping, constraining, and mediating the others. We saw this in Newton's second law, where time constrains the interaction between mass and acceleration to create force. The ideal gas law, where volume constrains pressure and temperature, keeping the system in balance. Maxwell's equations, where space-time constrains the dynamic relationship between electric and magnetic fields, allowing energy to propagate across the universe. In each case, the third element wasn't a passive backdrop. It was an active mediator, the force that allowed the other two elements to interact in a stable and sustainable way. This triadic balance doesn't just apply to physical systems, it applies to life itself. Biological systems, ecosystems, and even human societies are all governed by this same principle. In a living organism, homeostasis is achieved through the triadic interplay of genetic information, environmental stimuli, and metabolic processes. In economics, market stability arises from the balance of supply, demand, and regulation. In ecosystems, energy flows between organisms and their environments in triadic feedback loops that sustain life. The common thread is that balance isn't static, it's dynamic, constantly adapting to change. The triadic structure allows systems to remain flexible, adjusting as variables shift while still maintaining the overall stability necessary for survival and evolution. What we've uncovered through this exploration is a universe of homeostasis, where balance is achieved not through binary opposition, but through a constant interplay of three elements. Whether we're looking at forces, particles, or ecosystems, the same triadic patterns emerge, revealing a deeper, more integrated understanding of how complexity and stability arise. The triadic model doesn't just answer old questions, it opens up new possibilities. It encourages us to think in terms of systems and relationships, not just isolated components. It invites us to look for the hidden mediators, the unseen forces that bind systems together and enable them to adapt and thrive. So, what does this mean for how we understand the universe? It means that symmetry isn't simply about mirroring or opposites. It's about balance through dynamic interaction. And it's not just limited to the realm of physics. It's a universal principle that governs the behavior of all complex systems. By shifting from a dualistic view to a triadic framework, we're able to see the deeper structure underlying everything from the motion of planets to the flow of energy in ecosystems. It's a framework that gives us a more holistic understanding of the universe, one where balance is maintained not through conflict, but through integration and interplay. In this view, the universe is less a battleground of opposing forces and more a network of interconnected triads, each sustaining the others in a constant state of dynamic equilibrium. And this shift, from opposites to triads, offers us a new way of thinking about everything from particle interactions to human relationships, to the very nature of reality itself.